Welcome to the Journey to Chem. Today's warm-up is review, and we need to pay particularly close attention because that type of problem will be seen again. So please do the best you can, and we'll discuss it in a moment. Number one is a gas law part 2 problem. And first we must determine the moles of our compound that we're looking for. But we're given the mass of a different compound. And that makes me aware of the fact that we are having to change compounds, which requires a balanced equation. And we know that in combustion, and we're burning propane, we require oxygen, and the products of complete combustion are always carbon dioxide and water. I take the amount of the propane that I'm given and change it to moles. And in order to do that, I need the atomic mass units, the grams per mole. Well, we have 3 carbons, and each carbon has a mass of 12.0, and 8 hydrogens, which have a mass of 1.0 each. Then I multiply them again, and I add them up, and I get 44 grams of the propane for every 1 mole. And then I need to switch to carbon dioxide. Well, my balanced equation shows me that there are 3 moles of carbon dioxide for every 1 mole of the propane. And that's what I'm looking for. So I get 2.2840 moles of my carbon dioxide. Now, I'm given non-standard conditions, and therefore I'm going to need the ideal gas law. However, I did want to mention that if I was under standard conditions, then I would just go one more step and change it to volume. And 1 mole of any gas under standard conditions always occupies 22.4 liters. We call that standard molar volume. That's a little review for you. Well, I know that the ideal gas law is PV equals nRT, where P is pressure, V is volume, N is the number of moles, R is my ideal gas constant. We don't have to memorize that. We learned how to solve for that using standard molar volume, and you may want to review that before the exam. And the temperature is always in Kelvin. Now here I am solving for volume. Therefore, my volume equals nRT over the pressure. Well, the moles is what I solved for there, 2.2840 moles of my carbon dioxide. And notice when I'm in a calculation, I always take my values 4 significant places after the decimal. And then my R is 0.0821 ATM liters per mole Kelvin. And I'm using this particular constant because my pressure is given to me in atmospheres. And then my temperature is given as 35 degrees Celsius. So I must have 35 degrees Celsius plus 273. And that value then is 308 Kelvin. Then I divide it by the pressure, and I'm given a pressure of 3 atmospheres. The constant is very important to have. It is not standard pressure. It is a constant that we solved for. And when I do the math here, I get 19.2516 liters, and I'm asked for milliliters. And therefore, I'm going to go ahead and change significant digits that are required in the problem. The least number given in the problem were 2, because the 3.0 is 2 significant digits. And therefore, this is 19 liters. Well, I'm going to change it to milliliters. And I'm going to go ahead and erase this part. And let's just erase all of this. Make it nice and clean. We have 19 liters, and we need to change it to milliliters. You will need to be able to make all kinds of different conversions. Decimeters cubed, centimeters cubed, milliliters, and they're in 1 liter, I have 1,000 milliliters. And therefore my answer here is 19,000 milliliters of carbon dioxide. We try to be as concise as possible in our final answer. And that's how you do one of these problems at non-standard conditions. And I'll see you in a moment. In number 2, we are reviewing the shapes of molecules. Now on the final exam, you only have to know the 6 shapes that follow the octet rule. There will be no expanded octets, no exceptions to the rule. There are 6 shapes. They are linear, there are 2 different bents, trigonal planar, trigonal pyramidal, and tetrahedral. You are responsible for those. However, you will not need to know the specific angles. Well, this is a little bit of review here. Well, oxygen has an ending electron configuration of S2P4, which gives me 6 valence electrons. And then this oxygen also has 6 valence electrons. Now I use X's and O's. All electrons are identical. There is no difference. However, I like to know which atom those electrons came from if I'm going to be moving them around. Well, I see here that this oxygen only has 6 electrons and it needs 8. And therefore, I'm going to double bond with this oxygen here. I could have double bonded with this oxygen. It would be a resonance structure, and the actual molecule is an average of those 2 structures. Well, when I look at this, I see that I have 1 lone pair and 2 bond pairs, which gives me a bent shape. Bent 1 for 1 lone pair. And because it has this lone pair, it's very negative on this side where the lone pair of electrons are. It is pulling towards those electrons. And that would make it polar. The second case is very interesting. Well, sulfur also has 6 electrons. It is an S2P4 as well. It is my central atom. The first element given is my central atom. If it's not, then it would have to be underlined. And oxygen has 6. And again, I'm going to have to double bond here in order to get my octet around each one of the atoms. This has identical shape of the other one in A that we had. It has 1 lone pair and 2 bond pairs, making it bent 1. And again, because of this lone pair, it is polar. Then in the next one, we have chlorine as my central atom. And chlorine has an ending electron configuration of S2P5, which is a total of 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Now this -1 means I gained 1 electron, and I show that as a little negative to know that I took care of that extra electron. And then chlorine already has an octet, and therefore each oxygen is just going to share one of its pairs here, and that way it will get its octet. This shape has 1 lone pair and 3 bond pairs. And when we have a charge, I like to put it in brackets and show the charge that I took care of that extra electron. This shape is called Trigonal Pyramidal. And it's polar for 2 different reasons. First of all, it has a lone pair. And secondly, it's charged. And any molecule that is charged is always polar. Finally, I have nitrogen that has an S2P3 ending electron configuration. And that gives me 5 valence electrons. Now I know electrons like to be in pairs, so I'm going to move one of these electrons up here. And I have a -1 charge, which means that it gained 1 electron. And usually I put those around the central atom. Oxygen has 6. This oxygen, I'm going to go ahead and double bond it. And I need to make myself a little bit of room here. And it's nitrate. and the oxygen will be here. Now we have an octet around each atom. This shape has 3 bond pairs and no lone pairs. I need the brackets because it's a charged molecule. And this shape is trigonal planar. Trigonal planar. And it's only polar because it has a -1 charge. And anytime a molecule is charged, it is always polar. If it did not have that charge, then it has basically a non-polar shape. Because if we look at the shape of this trigonal planar, I can see that the bond pairs are equally pulling in all 3 directions, and therefore, unless it was charged, this would be a non-polar shape. And you will have shapes on the multiple choice section, as well as potentially on the problem section. And tomorrow, I'm going to refine the material that will be on the multiple choice. You have a sheet that gives you both a format that the exam is 50 multiple choice and 7 problems worth 50 points. And I'm going to narrow those multiple choice topics for you because we've covered an awful lot this semester. And I'm going to try to make it a little more specific so that you know exactly some of the things that you need to revisit. And we'll talk about that tomorrow. Well, that was some fun, and I know you're getting excited, just like I am. But I can't wait to see you tomorrow. Bye.
Thank you.